Hi, in this video, we will learn the laws of thermodynamics, the zeroth, first, second, and third laws. We will talk about thermal processes, and we will also learn the working principles of heat engines, refrigerators, air conditioners, heat pumps, and also we will learn the concept of entropy. So let's get started. So thermodynamics, it's the study of macroscopic variables such as temperature, pressure, and volume, and also average energy of the system and their relations, as well as heat flow. The Zeroth Law of Thermodynamics, it's very easy. If A and B are in thermal equilibrium, so you have two objects, A and B. If they are in thermal equilibrium, no heat will flow either way. And so thermal equilibrium means heat does not flow from B to A or A to B. So if they're in thermal equilibrium, then, and also if B and C are in thermal equilibrium, then the result or the conclusion here that we can derive is that A and C should be equal, should be in thermal equilibrium. So mathematically, we can write it this way: if A and B, the temperatures are the same, and if the temperature of B and C are the same, then from these two equations, you can derive this third one, which is the temperature of A is equal to the temperature of C. The atoms and molecules of any solid, liquid, or gas have kinetic energies due to their movements and vibrations. So if you have a solid, then there's this crystal structure, for example, ice. The water molecules, they do not travel, okay, but they can vibrate at their positions. So they can vibrate. But if you have liquids and gas, then those molecules, because now the bonds are really, really weak, then they can travel, so they can have kinetic energy from movements. And in the solid case, they can have kinetic energy due to vibrations. So in addition to the kinetic energy, they also have potential energy that arise from the chemical interactions between the atoms or molecules. So in the ice phase, there is these interactions or chemical bonds. In the liquid case, for example, water, there are still some bonds, some chemical bonds, hydrogen bonds between the water molecules, even though they are weak, but still they are there. In the gas phase, of course, there's no chemical bonds, but in the liquid and the water, in the solid case, there are chemical bonds. So they account for the potential energy. So if you think about the total energy, so the vibrations or the movement of the molecules, which is the kinetic energy, and the potential energy from the chemical bonds, the total energy, if you add them up, the total energy is called internal energy, and it's shown by U. So when we did mechanics, we used U for potential energy sometimes, or gravitational potential energy, but in this video, we will use U, uppercase U, as internal energy, which means kinetic energy plus potential energy. And it's always a positive quantity. So heat, on the other hand, it's shown by Q. It's still energy, but we call it heat because it's heat given to a system increases its internal energy. So heat is an energy that you can give to a system or take out from the system. For example, if you have a gas here, then you can heat it up. So how do you give heat? You can maybe use a fire here. So you can give heat to it. If you give heat to it, what will happen? It will increase its internal energy. So again, internal energy means kinetic plus potential energy, and potential energy is from the chemical bonds. So the change in internal energy is basically the final minus initial, and it will be equal to Q, which is the heat provided to the system. So then one of the things that you can do to increase the internal energy of the let's say if this is gas or liquid or ice, doesn't matter. If you want to increase the internal energy, for example, if you want the molecules to vibrate more or move faster, then you have to add heat to the system. If the system takes energy in, as I described here, so delta U and Q will be positive. So that's the definition here. And if the system loses energy, delta U and Q will be negative. And you can actually see it here from here. So if Q is positive, so you are giving system some energy to the system. So the final minus initials, well, it should be positive, right? Because the final internal energy should be positive because we gave the system energy. So to be mathematically consistent, so we have to make these definitions. So if the system takes energy, then delta U and Q will be positive. So whenever you see a system which takes in energy, then in the equations, we use for that Q positive value. But if the system loses energy, if energy comes out of the system, then for Q, we would use a negative sign. So it will be a negative number. The gas in the container pushes the piston. So if you look at this picture, there's some gas. It pushes the piston up all the time. Because whenever there's pressure inside, it will always push the piston up. So maybe there's some weight on the piston. The piston so there may be some equilibrium. But the force that the gas applies on the piston, it will be always in the upward direction. So if the piston is left free to move, it will move up, it will go up. The force and the displacement will be in the same direction. So the force from the gas on the piston, it's in the up direction. And if the piston moves up, so the displacement is also in the upward direction. Now, if you remember the definition of work, it's F dot product. And this would bring a cosine theta term, if you remember, times d displacement. So these are actually vectors. So when the force and the displacement, when they're in the same direction, then the work is positive. So work done by the gas will be positive in this case, because the force is always up and the piston moves up, so the work will be positive. Now, since the gas here did work on the external world, it lost energy, which went into the atmosphere. So the gas makes work on, you can think of on the piston, and the piston pushes the air in the atmosphere. So the gas actually loses energy. Now, since the internal energy of the gas decreased, so delta U, which is final minus initial internal energies, it should be equal to, so the change in internal energy, it should be equal to negative work. Now, again, why do I put a negative sign here? Well, the work in this case is a positive number, okay? But when the system makes work, then when the gas makes work, it actually loses energy. It's using its internal energy to do work, so its internal energy should decrease. So if we don't put a negative sign here, because work itself is, in this case, positive number, then it would correspond to increase in internal energy, which is not correct. So that's why we put a negative sign here. Now, if someone pushes the piston down, as you can see in the animation, the work done by the gas is negative. Since the force on the piston due to the gas is upward, as I described always, this gas is always pushing the piston in the up direction, but the piston goes down. So the displacement here is in the down direction. Now, what happens if the force and the displacement are in the reverse directions, in the opposite directions? You get a negative sign here. So now in this case, the work is a negative number. So it is a negative value. So now if you consider again the change in internal energy, we write the same formula, we don't change the formula. And you will say it makes sense because work is negative here. So delta U, in change in internal energy, should be positive. Why? Because this is a negative number now. And there's another negative number. So this, the right-hand side, is positive number. So the change in internal energy is positive. That means internal energy increased. Is that really the case? As you can see in the animation, the blue color, you can think of it as cold, and it turns into purple or close to red, maybe. So as you compress the gas, it actually heats up. So the internal energy increases. And compressing a gas is like hitting the gas particles with the piston, so giving them extra kinetic energy. And what happens if you increase the kinetic energy, then you increase internal energy, because internal energy includes kinetic energy and potential energy. So when you push the piston, you can think of it as you are hitting the gas molecules with certain speed. So you are imparting momentum to the gas molecules, which increases their kinetic energy, hence their internal energy. But this formula is always valid in each case, whether the piston goes up or down. The change in internal energy is always equal to negative times work. So the internal energy, it's the internal energy of the gas, okay, not the piston, internal energy of the gas. And the work is the work done by the gas. Here, gas did work, so it was positive. Here, the work done by the gas was negative. You can think of this way, some work done on the gas. That's also another way to think about it. Or you can look at the directions of F and displacement. And if they're in the opposite directions, then you can say that the work is negative here. Okay, now if we combine these two equations, so this is, as we talked about it, if heat enters the system, then that increases internal energy. So we would say heat is positive. So if system gains heat, then we are using a positive value for Q. If system loses heat, we are using a negative value for Q in the equations. And for the work, if the gas does some work, then so this is work done by the system. You can think of system as the gas. So if the gas does some work by pushing the piston up, then work is positive. And if the outside world, like someone pushing the piston down, then that's work done on the system or on the gas, then we use negative, for work, we use negative value. But if we combine, so in the previous slide, we talked about these two equations. Now, if we combine these two, we get the first law of thermodynamics. It's change in internal energy of a system is related to heat flow That's the first part, or this one. In or out of the system, and the work done by or onto the system. So then that's the second part, or this equation. Now, if you combine these two equations, this is the first law of thermodynamics. So this is the most general case where you can push the piston or pull the piston up, or the gas may be pushing the piston up. And at the same time, if Q is, if heat is entering the system or coming out of the system. So if both heat and work is present, are present, then you can use this equation, which is the first law of thermodynamics. So now we will talk about some thermal processes, and in those thermal processes, pressure, volume, temperature, some of them will change and some of them will be constant. So let's start with the constant pressure volume expansion process. So constant pressure process. Okay, so how can you keep the pressure constant? So, and by the way, so we are talking about gases here, so we always have the PV and KT, so the ideal gas law. So we will keep this pressure constant, but the other things can change. So volume can change. We will also keep number of molecules or atoms in the gas constant because we have a closed container. N cannot change, so the number of molecules or atoms in the gas cannot change, but V can change, which is the volume, and T, temperature, can also change. Okay, K is Boltzmann constant, it's some number, so it doesn't change either. So in this case, if the piston moves out, so the volume is, so initially the piston was here, so there was this gas. Now the piston is going out, so the volume is increasing. The volume will increase and the pressure will drop. So normally the pressure would go down if you increase the volume. And you can also see it from here. If pressure goes up, the volume naturally it may go down if the right-hand side is constant. But you can actually have, so you can have the piston go out, but at the same time, there is a way to keep the pressure constant. But we can keep the pressure constant at P0 by heating the gas at a specific rate. So the volume is increasing, the pressure will go down normally, but if you heat the system, if you provide heat, which is going to be this Q here, then you can at the same time keep pressure constant. But of course, you have to heat it at a specific rate so that the pressure doesn't go up or down, so it stays constant, but in principle, you can do it. So if pressure is constant, then let's calculate work done by the gas at constant pressure. So work formula is F times displacement. So F is the force from the gas on the piston, and the displacement is, this is displacement of the piston. So force can be written as pressure times area. So we have, and pressure is constant, which is at P0, PA. Now if you combine this A and those X values, what happens if you multiply the base and the height of a cylinder? Well, you find the volume, right? So the final volume and initial volume. And I can write this change in volume as delta V. So this will be the work done by the gas at constant pressure. And if you plot PV graph, so the pressure versus volume graph, and since the pressure is constant, this process the graph will be like this. It's just straight line. So the volume, initial volume, final volume is increasing, but the pressure doesn't go up or down because we are heating it at a constant, at a certain rate so that the pressure stays constant at value P0. Now, you can see that this actually, P0 times change in V, is just the area of this, it's basically the shaded area. So you can either use this one, or you can, if you are given the PV graph, you can calculate the area under this line to find the work done. So this is work done. So this area gives the work done. Now let's move to non-constant pressure volume expansion process. Now here, when both P and V changes during the process, so that process could be this piston is going out. So maybe there's some heat, or maybe there's no heat. But the point here is the pressure is not constant in this case, because now non-constant pressure. When both P and V changes during the process, to find the work done by the gas, so work done by the gas is actually internal energy the gas loses. You have to calculate the area under the curve or line in the PV plot. For example, we have this plot given. It's again PV graph. But the pressure, as you can see, if while this piston is moving, so the volume is increasing, volume of the container or the gas is increasing. And in this case, the pressure is also increasing. How is it possible? Well, you need to provide heat at a specific rate, where now the pressure is not constant, but it's even increasing. So as shown in the graph, the gas expands and its pressure is also increasing. So heat must have been given into this system. What is the work done by the gas? How do you calculate work done? So to be able to calculate work done, now we cannot use work equals F times displacement, because if you remember from the physics 1 lectures, this is valid only when F is constant. And F is here P times A. That also means pressure is constant. What do you do when force is not constant? You don't use this equation, but you can still calculate the area. So you can use the plot to calculate the area, which will give you the work done. So the work done in this case is this whole area under this line, which if you calculate it, it's 3.7 10 to the 4th joules. Okay, so we did constant pressure and non-constant pressure processes, and we learned how we can calculate the work done by the gas on the environment, which is in this case the piston. Now let's move from constant pressure to constant volume processes. So in constant volume processes, as the name suggests, the volume will not change. That means there's no piston. We just have a closed container. Since there's no piston to move here, well, there's really, the walls are not movable. So then the gas cannot do work, because work is related to force and displacement. Because there's no displacement here, there's nothing that moves that can create displacement, then the work in this case is 0. Now the first law of thermodynamics, which was this, now reduces to this, which means if you want to change the internal energy, the only thing that you can do in the constant volume processes is either to give heat to the system or take out heat from the system. And if you look at this graph here, let's see what happens. It's the pressure volume graph again. And the volume doesn't change, as you can see, because there's no piston that can move. So the volume is constant. This is a constant volume process. And the pressure goes from initial value to final value. So the pressure, according to the plot, the pressure is increasing. How is it possible? Well, if you heat the system, you know, from maybe the pressure cookers, if you heat the system, you actually make the atoms or molecules of the gas move faster. That means you give them more kinetic energy, so they are hitting the walls with more force or more momentum. That means you increase their pressure, and you can do that by giving heat to the system. Okay, so in general, a gas may go through several different processes. So we talked about constant volume and constant pressure so far. So it doesn't have to be only either one of them. It can be a combination of them. For example, in this plot, again, PV plot, the process one, this part, gas expands and pressure increases. As you can see, gas, the volume is increasing, so gas is expanding, and the pressure is increasing as well. So in this case, heat must have been given to the system, otherwise expansion would decrease the pressure. So if the volume is increasing, so definitely there's some kind of piston. So we have a container now with a piston that can move up or down. In this case, if the gas is expanding, normally the pressure would go down, but because the pressure is also increasing, then that means there's some heat given to the system. And if you want to calculate this, the work done by the gas on the piston, you can calculate basically this area. So area of the triangle. Now in the second process here, gas at constant volume, you can see that the volume is 0.5 meter cube. It doesn't change during this the second process, which just increases the pressure from 140 to 210 kilopascal. So, but the pressure increases, so how is it possible? As we discussed here, if you want to increase the pressure, heat, either you have to compress the gas. In this case, the volume doesn't change, so you're not really compressing it. So the only option left is you add heat to the system. So there's no work done because the volume doesn't change. So the piston is not pushed or pulled, but heat is given to the system, which increases its pressure. Now in the third process, which is the constant pressure, because the pressure doesn't change, that's the process that we talked about in the previous slide. The pressure doesn't change, constant pressure, but the volume is increased. So if you want to calculate the work done during the third process, you have to calculate the area of this rectangle. So the area of the rectangle will give you work done during process 3. And the total work will be W1 plus W2, which will give you, in this case, 80,500 joules. And as you can see, during process 2, there's really no work done because it's a vertical line, so there's no area under it. Now, another process is called isothermal. So iso means equal or same. Thermal means temperature. So isothermal constant temperature process. Let's again remind ourselves the ideal gas equation. Now, this is constant. T is constant. So this is constant. K is already constant. N is number of molecules is already constant. So what can change is just P and V values. So temperature of a gas in a container may be kept constant if we place it in a liquid heat bath. So now what I'm explaining here is that how can you keep the temperature of the gas constant while its volume is increasing, its pressure is changing, but how is it possible to keep the temperature constant. The idea is you put this container in a liquid, and that liquid is always kept at the same temperature. So the gas exchanges heat. So sometimes it can take heat from the water or give out heat to the water. With the liquid, so gas temperature stays constant. So that the gas temperature always stays constant. So you can think of this heat bath or the liquid here. Its mass is huge, so you can think of that it's the change of gas. So when the gas takes heat from the water, if the water is if its mass is so large, then the temperature of the water will not really change. Or if the system gives out heat to the water, again, if the mass of the water is very large, then that heat coming from the gas to the water will not really change the water temperature. So the idea is here is the heat bath is using water or any other liquid with a large mass in comparison to the mass of this container, so that the temperature of the container will be always at T0. Now imagine the temperature of the container going down. What would happen? Let's say this expands and the gas here cools down because the volume is increasing, the pressure goes down. But in this case, if the temperature goes down here, because the container and the water, they are in contact, so heat will flow from the water to the container. If in any case, for some reason, if the temperature increases, if the gas temperature increases, then that extra heat, so in this case, the temperature of the gas would be larger than the temperature of the liquid, then heat will come out from the gas to the liquid. So the idea here is that the gas temperature in the heat bath will be always the same. Okay, so if the temperature of the gas is constant, which can be kept by means of a heat bath, then what we have is, let's write PV equals NKT. If this part is constant, then I can write just constant here. So we have P initial, V initial constant, and it will be also equal to P final times V final. So from here we can write P initial times V final equals P final times V final. So let's say initially the pressure and the volume is like this, and then the piston moves here. So now the volume is larger and the pressure will be actually less. So those values will be P final and V final. Of course, pressure and volume changes, but what doesn't change in isothermal processes, because temperature is constant. So because this is constant, and so the right-hand side is constant, what doesn't change is the P times V value. So here both volume and pressure change, but they cannot change arbitrarily because there's a constraint between P and V that's given by this equation. So what it means is if pressure increases by a factor of 2, then the volume should decrease by a factor of 2. So because of this constraint, they cannot change arbitrarily. For example, if pressure increases by a factor of 3, volume cannot decrease by a factor of 2. So it should decrease by a factor of 3 as well. So there's this constraint between P and V that's put by this equation. Now in the graph, different curves correspond to different constant temperature values. So if PV is constant, let's write just C. So that means P equals something like C divided by V. And from maybe calculus, you remember this is an equation like Y equals 1 over X. And the graph of 1 over X is something like this. And the reason that we have different curves is actually if you change this constant here, and you remember that constant was N KT. So we actually have here N KT. T is constant, but for different values of the constant temperature, you can have different curves. So if you have a setup like this, then these different values would be corresponding to different temperature values of the heat bath and the gas. But once you set up the system, let's say you set up your system at 700 Kelvin, then the only relevant curve here is this. So what this means is you can increase the pressure to 15 and the volume would be 0.5, or you can decrease the pressure to 5, which I have to use this 700, this one, and that means the pressure would be about 1.25. So this curve is actually giving you P equals constant divided by V, which is, in other words, PV equals constant curve. Now, how do you calculate the work done in this case? So at constant temperature, this piston is moving out. By the way, so there's really no water force, the force from the water here. We could draw this, maybe we could draw this as a piston, as a container like this, so the water doesn't go in. So the only idea here is that in a heat bath, you can keep the temperature at constant value. Anyway, so if you want to find the work done by the piston on the atmospheric gas here, as the gas pushes the piston out, is again, you have to calculate the area. For example, if the volume goes from, let's say, again, let's use the 700K curve. So it's about here. So if the volume goes from 0.5 to 1.5, then you would calculate the area under this curve. So this area here would give you the work done by the gas on the piston. So again, you can use the PV graph. Now, as we mentioned, this curve is P equals some constant divided by V. Now you can calculate, you can use calculus. You have to use actually calculus to be able to calculate area under the curve. And but we will skip the details. So if you use the integral from the initial volume and final volume, the area under the curve will be given by nkt. Remember, this constant is, this is actually nkt. So this is coming from PV equals nkt. And if you calculate this area by using integral, you will find log V final divided by V initial. Or we can rewrite uppercase N, K as N, lowercase n, which is actually N divided by Avogadro's number times R here. And if you remember, this thing was actually K, same thing. Okay, so So you can either use this form, uppercase N KT, or you can use lowercase n RT. If you have mole, given the particle number in terms of moles, then you would use the second form. And if you're wondering where this natural logarithm, so ln means log in the base e. So it's actually coming from the integral of this curve. Again, this curve is like 1 over x, y equals 1 over x. In this case, y is pressure, x is volume. And if you take the integral of this, you will find a natural logarithm, which is ln here. Okay, here's an example. A cylinder holds 0.54 mole of an monatomic gas. So because it's given in moles, so we have to use the lowercase n. When we use, if you're going to use the work equation formula or ideal gas, so you have to use the mole. So we will use then this form because this one includes the lowercase n. Ideal gas at a temperature 310 Kelvin as the gas expands isothermally from an initial volume of 4.2 10 to the negative third meter cube to a final volume of 6.8 10 to the negative 3 meter cube. Determine the amount of heat that must be added to the gas to maintain a constant temperature. Now, let's first use the first law of thermodynamics. So we can rearrange this, so we can rewrite this as Q equals change the heat equals change in internal energy plus work. And the change in internal energy is, if you remember from the earlier chapters, 3/2 nR delta T. In this case, the temperature does not change because it says constant temperature. So this will be 0. So the change in internal energy is 0. Does not change since the temperature is constant in isothermal processes. And you can, for the formula, you can go back to chapter 17. Now let's calculate work. So basically, we are going to calculate the heat given to the system because that's the question. Determine the amount of heat that must be added to the gas. So to calculate heat, we found this is 0, but now we have to calculate work. For work, we use this formula. So work done in isothermal processes. But again, this formula is only valid for isothermal processes. In other processes, there may be other formulas, as I mentioned, but one technique always works, which is basically calculating the area under the curve. It always works. So if you plug in numbers, the work done by the gas on the piston as it expands is 670 joules. Now to calculate the heat that must be added, you have to use, so this is basically, again, remember, the first law of thermodynamics. And because this term is 0 and heat would be equal to work in this case, which is 670 joules. So you have to add Q equals 670 joules so that the temperature stays constant as this gas expands from this volume to this volume. Okay, now this is the fourth process. It's called adiabatic process. It actually means now the heat is not exchanged. So remember, we had a process where it was, for example, at constant volume. So there was no piston to move up or down. In this case, work was 0. But in adiabatic processes, there may be a piston, as you can see here. But now the system cannot exchange heat with the environment. So how is it possible? Well, it could be possible if you use an insulation, so that the gas cannot exchange heat with the environment. And adiabatic means not passable. When the gas cannot take heat or give out heat, heat does not pass. So not passable, adiabatic, heat does not pass. Same thing. So it's called an adiabatic process where Q is 0 in these processes. If the container is insulated, the gas will not exchange heat with the environment. Then the first law of thermodynamics, well, because now this is 0, we get the change in internal energy is only possible if the system does work on the piston, if the piston does work on the system, as if someone pushes it down. Now, here's an example. When a certain gas is compressed adiabatically, so here's the case, someone is pushing it down, it's compressing, but in the meantime, the system, the gas cannot exchange heat with the environment because it's an insulated container. So it's compressed adiabatically. So the amount of work done on it is 730 joules. Find the change in internal energy of the gas. Now, since the heat here is 0, there's no heat exchange because of the insulation. So this is an adiabatic process. We only have work. And so if the system, if the work done, if you do work on the gas, remember, that's a negative number. So when the work done on the system, it's a negative number. And there's an extra negative number here from the formula. If you multiply these, you get a positive number. So this is the change of internal energy. Let's see if it makes sense. If you compress a gas, what happens? You are actually, the piston is hitting the gas particles even more. So the piston is moving down with certain momentum. You can think of that way. And the gas particles and the piston, they are colliding. So this is kind of, this is a collision, inelastic collision. So the piston gives its energy or momentum to the gas particles. So the energy, kinetic energy of the gas particles increase. And that means the internal energy increases. And so that's why we have a positive number here. Remember, final minus initial. If you have a positive number here, that means the final is greater than initial, and that means the internal energy increased because the final is greater. Now, if there's no insulation, but if an expansion or compression happens quickly enough, there's no time for heat flow to occur. And these processes are practically adiabatic. So let's say you have this tube and you will hit it, and within the tube there's some piece of cotton, okay? And if you compress it really, really fast, now because the process is really fast, if it happens quickly enough, the heat, there's no time for the heat to go out because the process happens very fast. So what happens to that energy? Well, that energy build up inside is actually, it is able to fire up the cotton. Again, when you hit the pump, you are actually giving kinetic energy. This is an inelastic collision. You are giving energy to the gas particles. And so that build-up energy is enough to fire up the piece of cotton. Now, if you do this process, if you compress it slowly, you cannot fire up the cotton. The reason is that if you do it slowly, the build-up energy will actually go out to the system. So if you do it slowly, the gas inside and this container, they will always be at the room temperature. If this is 20 degrees Celsius, the gas will be always at 20 degrees Celsius because it's interacting with the environment. Even if you try to heat it up, it will lose heat to the environment. But if you do it really quickly, now there's no time for the heat to escape. Even though this is not insulated, but because there's no time for the heat flow to occur, these processes are practically adiabatic. So the heat exchange does not happen. So again, what happens to that heat? It actually builds up and it can fire up the cotton. So this is called adiabatic heating, when a piston that fits snugly inside a cylinder is pushed downward rapidly. So to do this rapidly is important so that no heat exchange happens with the environment. The temperature of the gas within the cylinder increases before there's time for heat to flow out of the system to the environment. Thus, the process is essentially adiabatic. As a result, the temperature of the gas can increase enough to ignite the piece of cotton in the cylinder. In a diesel engine, the same principle is used to ignite an air-gasoline mixture without a spark plug. Okay, so now let's talk about specific heats for an ideal gas. Now, if you remember from earlier chapters, a specific heat shown by lowercase c of a substance is the amount of heat needed to raise the temperature of 1 kilogram of the substance by 1 Celsius degree. Now, for gases, we did this for liquids and like ice, water, but we have not really talked about gases in the previous lectures. But here, let's talk about specific heat for gases. And for gases, there's two different specific heat values. One is for constant volume processes, and the other is for constant pressure processes. So specific heat for constant volume, you basically add a V here. This means this is the specific heat, but the volume is kept constant. And you know that CV is used in these equations. Let's say you have gas, and it has certain mass. So let's say its CV is given. The question could be, how much heat is needed to raise its temperature from 10 to 20 degrees, for example? Now, we will make one more definition here, which is molar specific heat for constant volume. So this was constant volume as well. Now we will do molar. We will add molar specific heat, and we will show it with uppercase C. Now, why do we do that? Because usually the gas mass is not given. What's given is usually the moles, the number of moles of gas. So to be able to use number of moles in this equation, instead of mass, we will have, instead of specific heat, we will have molar specific heat. The reason that it's called molar, because it works with a lowercase n, which is for number of moles. Now there's one caution here. Don't confuse this uppercase CV here with the heat capacity that appeared in chapter 16. So these are different things. Okay, now let's move to constant volume processes. Now in constant volume, there's no work. So work is zero because it's the container doesn't have any movable parts like a piston because it's constant volume. So the first law of thermodynamics becomes delta U, change in internal energy equals Q, which is heat. So we are still talking about constant volume here. For monatomic gases like helium, neon, argon. So for these monatomic gases, the monatomic means single atom. They are not polyatomic. Poly means many. So for example, hydrogen gas, carbon dioxide, these are polyatomic gases. We will not talk about these here. But let's talk about monatomic gases. We have, from chapter 17, if you remember, internal energy is 3/2 NKT. N is the number of molecules. And you know that N can be written as lowercase n times the Avogadro's number. And if you combine Na and K, you can also write this as R, which is the gas constant. So now we have U, and you can write delta U by basically putting a delta in front of T. And we also, so this is the first law of thermodynamics. So we can use this one here. And this is also something that we learned in the earlier chapters, the heat required to increase the temperature. And we can use that formula here. And if you equate those two, you find CV for monatomic gases to be 3/2 R. So it turns out it's a constant number because R is, it's just a gas constant, it's just a number. So CV, molar specific heat, becomes just a constant number for monatomic gases. For polyatomic gases, for other gas types, then it will be some different number, but not exactly this. So this is valid only for monatomic gases. Now, we talked about constant volume here. Now let's move to constant pressure for a monatomic gas. Now we have constant pressure. Well, there's a piston that can move up or down. It doesn't say constant volume, so there should be some work. Pressure is constant, but volume can change. And we can write it as nR delta T, because PV equals nRT. If you remember, we are using gas equation here. Ideal gas law, PV equals nRT. So P delta V, which is work, is actually equals nR delta T. And the first law of thermodynamics, now in this case, because it's not constant volume, there's also work. So it will be Q minus W, which is work. And we also have this one, which is the heat required to increase the temperature of gas. And U, as we mentioned here, is, again, 3/2 nRT. Now, if you combine all of these, you will find molar specific heat, now in this case for constant pressure for monatomic gases. And it turns out that it is 5/2 times R. It's again a constant number, but it's different than the value of constant volume molar specific heat. So you have to use the CV, molar specific heat, for processes where the volume is constant. But if volume is not constant, but the pressure is constant, then you have to use this value. And again, when you use these values, when you want to calculate heat required to increase the temperature of a gas by delta T. So they come in here into this equation. Okay, now we will use those Cp and Cv values that we learned in the previous slide. But before that, remember that temperature in isothermal processes, it was constant. So when this part of the gas law is constant, we can write, so we know that PV, P and V, they can change from initial to final, but this multiplication is always, it's always constant, it's always the same. So for example, P and V can be 1 and 3. And P final, if this is doubled, let's say it goes to 2, then V final should go, it should decrease by a factor of 2. So this multiplication is 3, and here the multiplication is 3. So P and V can change, but PV, P times V is constant. But this was valid for when T is constant. By the way, N and K in these in this lecture, we take them to be, K is already constant, it's just a number. And in this lecture, we take always N to be constant. We don't, we assume that the number of molecules does not change in any way because they are in the gases in the container. So this was for isothermal processes where it is T constant. But what happens in the adiabatic processes? Adiabatic process means Q equals 0. So the heat does not go into the container. So the only thing that can happen is the work. So this piston may be pushed up or down. So there is work, but there's no heat that goes into the system because it's insulated. Okay, so in adiabatic processes, by using some, so the question is, can we get something like this for adiabatic processes? This is for isothermal processes when T is constant, but can we get a similar equation for adiabatic processes? Now, by using some calculus, which is script here, you can show that PV and KT, here now the constant, if you put T here, what's left on the right-hand side is N times K, which is constant. So PV divided by T is constant, even though each one, PV, T, they can change in the process, but this combination PV divided by T is constant. And by using the fact that Q is 0, now you do some math here, and what you derive is actually P times V to the power of gamma is constant. So then I can write this as initial and final. So the difference between the adiabatic process equation and the isothermal process constant temperature equation is actually in the adiabatic processes you have gamma, the exponent gamma on top of the volume. And what is that gamma? It's Cp divided by Cv. So it's basically molar specific heat at constant volume, which is in the denominator, and the molar specific heat at constant pressure. So it's the ratio of them. Okay, so for monatomic gases, we know what these values are, so we can calculate gamma. We learned Cp is 5 divided by 2R, and Cv is 3 divided by 2R, so R's cancel, 2's cancel. And gamma for monatomic gases turns out to be 5 divided by 3. Again, what are those gases? For example, helium, neon gas, argon gas, so some other noble gases. But for polyatomic gases, like for example, carbon dioxide, hydrogen gas, they always come as 2 hydrogens, not single hydrogen. So for those gases, those gamma values are different, so you have to look them up if you need them. Okay, so we also got the equation for adiabatic process. So depending on the problem, if it says isothermal process, you would use this equation. If it says adiabatic process, then you would use this equation. Okay, in this example, let's read it. A container with an initial volume of this holds this much moles of a monatomic ideal gas. So from here, I can say that then the gamma value is 5 divided by 3, as we calculated in the previous slide, at a temperature of 325 Kelvin. The gas is now compressed adiabatically, so you have to look for these keywords. So adiabatically, then when you see that keyword, then that means you have to use this equation with the gamma. So the volume, so it expands to this volume. Find in part A the final pressure, and in part B the final temperature of the gas. So first find the initial pressure, because the initial pressure is not given, the volume is given, the temperature, so PV equals nRT. Moles are given, temperature is given, R is constant, volume is given, but the initial pressure is not given. But I can use ideal gas law to find the initial pressure, which turns out to be 109 kilopascals. Now in the second step, so now I know the initial pressure, initial volume, okay? I know the final pressure, which is given here, sorry, final volume. Well, what's not given is the final pressure. That's actually what I'm going to calculate. So I'm going to calculate final pressure. So just solve for final pressure and plug in the numbers. This is the final pressure. Now look at the pressures. This is initial, this is final. If you compress the piston, that makes sense, the pressure goes up. Now finally, find the final temperature. Again, we will use PV and RT. So now in this case, for final values. Okay, so final temperature, we don't know. Final volume, we know this, it's given in the problem. Final pressure, we calculated here. And all you have to do is here to solve for final temperature. And it turns out to be 446 kelvins. So you did work on the system, you compressed it, and you would expect the internal energy goes up. So the temperature, that also means the temperature goes up. And you can see that the temperature increased from 325 to 446 kelvins. Now, let's move to second law of thermodynamics. It's about heat flow. When objects of different temperatures are brought into thermal contact, let's say you have hot and cold objects, and if you connect them with some other material, so basically now there's thermal contact, so the hot molecules will actually make these molecules here move faster, so it will basically, the heat will flow from hot to cold. The spontaneous flow of heat. Now, spontaneous means without outside cause, naturally. So the spontaneous flow of heat is always from high temperature object to the low temperature object. Now, spontaneous heat flow never proceeds in the reverse direction. So if you leave two objects in contact, hot and cold, you never see heat from cold object going to hot object. In that case, the cold object would become even colder and hot object would become even hotter, but that doesn't happen spontaneously. So it doesn't happen naturally or without any other outside cause. So basically, again, the second law of thermodynamics is that heat flows from hot objects to cold objects. So ice melts spontaneously at room temperature as per the second law of thermodynamics. Because the room temperature is hotter than the ice, so the heat flows the hot room air into the ice. Okay, now we can ask this question: does a freezer violate the second law of thermodynamics when it converts water to ice? The answer is no. The freezer is using energy, it's using electricity. So it's not a spontaneous process. The freezer is actually, it's a machine. It doesn't happen naturally. The water doesn't turn into ice in a freezer naturally. It's actually, the freezer is using work, using energy. So going back to the second law of thermodynamics, as you can see, it talks about the spontaneous or natural heat flow. If you use a freezer, you don't violate second law of thermodynamics, because in the case of freezer, you are actually using energy or work to turn water into ice, which is not a spontaneous process. Okay, now we move to heat engines. So heat engines, they basically convert heat into mechanical work. So one example to heat engine is the trains with using steam. So they basically use coal and to create some fire. And that fire in the boiler, it heats up the water, so you get water steam at hot temperatures, and it's used to move the train. So that's an example of a heat engine. So in heat engines, the gas should flow. So basically here you're utilizing the pressure or the pushing force of the steam. So in a heat engine, the gas should flow and push the piston and create mechanical work. So hot temperature or hot gas is not just enough, so it should be able to flow. When it flows, then it can push the piston or it can do work. So for gas to flow, temperature difference is needed, hot and cold. And we will see in the diagram, we have cold temperature and hot temperature, and the gas flows from hot temperature to cold temperature, and in the meantime, it pushes the piston and does some mechanical work. But what happens if both are, the condenser and the boiler, if they are at the same temperature? Well, you can have hot gas, but it will not flow. And if it doesn't flow, then it would not do any mechanical work. It will not push the piston. So what you need is not just hot temperature, you actually need temperature difference, hot and cold. This point is important. So an analogy to it is that to create electric current, potential difference is needed, which is called voltage. For example, a battery has potential difference between its positive and negative poles. Now here's a diagram of a heat engine. Let me explain how heat engines convert heat to mechanical energy. Remember, heat engine converts, it takes, so if this is heat engine, it takes heat and it produces work, mechanical work. So first you have some water here and you heat it up. You heat, so you basically use fire, maybe you're using coal. So you give heat to water. So here's the boiler. It's at hot temperature. TH means hot temperature. Boiler is at hot temperature. So water absorbs heat, which is QH. So heat is Q. H means the subscript H. It means heat. Sorry, it means hot. So water absorbs heat, QH, in the boiler, and hot steam is formed. So now you have steam, hot steam. Now, hot steam flows to colder regions where the condenser is. You have a condenser here. It's at a lower, colder temperature. It doesn't have to be below zero or close to zero. What matters is the temperature difference. Remember, when the heat flow, also the particles also flow, in this case the steam, from hot temperature to cold temperature. When you have a temperature difference, you will get a flow. So hot steam flows to colder regions where the condenser is, and on its way, the pressure of the hot steam pushes the piston and it creates mechanical work. So as the steam comes down, moves because of the temperature difference, it will also push the piston out. So you will get some mechanical work. So you can use that to move your train or ship, or you can use that work, for example, to take water or gasoline from the ground. So you can use it for any purpose. Now, at the cold condenser, hot steam loses heat. So when the heat comes here, there's the condenser. So that steam gives out heat to the environment. And then what happens if the steam gives out or loses energy or heat? Well, it turns into water. Why is the steam losing heat? Because it's colder here. The condenser is at cold temperature. And cold water is pumped back to the boiler. So you have a pump here. It pumps back the cold water back to the boiler. And this cycle continues like this. So heat is given to the system, and the system does some work and also gives out some of this heat to the environment. So work that the heat engine creates is the difference between absorbed and given out heat. So the work that you get out of the system is the heat given to the system minus the heat that the system gives out to the environment, which is Q, the heat given to the environment at the condenser. So this also shows us the energy conservation. Now, there may be so many different engine designs of heat engines, but the thermodynamics of the heat engines depends only on the fact that the heat engine takes heat from the hot reservoir, this one, and produces mechanical work, here, this one, and gives off the remaining energy to the cold reservoir, which is this one. So the heat engine depends on, so the only variables of a heat engine is these three values, not the details. So instead of this diagram, then we can use this diagram. So we have the hot reservoir, which is at temperature TH, and the engine takes energy. So again, this is like, it could be a fire, for example, in the boiler of a train. So the engine takes heat and then does some work as shown here. So it does some work. And then the engine, in this case here, the steam, it gives out energy to the cold reservoir. And this could be maybe the temperature outside the atmospheric temperature. And this QH, so the energy conservation is here. So QH is taken from the hot reservoir, and some of it is turned into work. And the remaining part, this QC, is given to the hot reservoir. So from this point on, instead of using this diagram, we will use this simpler diagram for heat engines. Let's define efficiency. So efficiency is shown by lowercase e of a heat engine, quantifies its ability to convert the heat added, which is QH here, to the engine into work W here. So the efficiency is basically how much of this energy added to the system, or that the engine takes from the hot reservoir, can be turned into work. Okay, not all of it is turning into work, because some of this energy, some of this heat goes out to the cold reservoir. So that means this is kind of, you can think of this as a wasted heat. So this is the valuable one, because it's work that you can use to do several things. So the efficiency is basically the efficiency of this conversion, the heat added to the system to work. So, and the definition is here. So E is some number between 0 and 1. If it's 0, that means the engine cannot do any work. It cannot produce any work if it's 0. If it's 1, that would mean the engine could convert all the energy, all the heat that it takes into work, but it's not, as you will see in a second, it's not possible. It cannot be 1 for the heat engines. So it's some number between 0 and 1. The greater the E is, the greater the efficiency is. Now, this is the definition. Now, you also use, along with this definition, if you also use the energy conservation, remember this is actually the same equation here, energy in and energy out. When you use these together, you can write E. So from here, you can write E equals work divided by QH, which is this part. Now, instead of work, you can plug in these values. You can write it as QH minus QC divided by QH. And if you divide this part and this part separately, so if you separate the two terms, so it turns out to be 1 minus QC divided by QH. And from here, you can see that E cannot be 1 unless QC is 0 Kelvin. By the way, these are, if QC is 0, which is not possible, there is always some heat which is given to the system. So because this term is not 0, efficiency is never 1. So for example, if efficiency is 0.2, we say that the engine is 20% efficient. In this case, 20% of the input heat, which is QH, is converted to work. So work equals 0.20 times QH, and 80% goes to waste heat, which will be here. So if the efficiency is 20%, then so if this is 100 joules, then you do work. This engine creates work for 20 joules, and 80 joules is wasted. It goes into a cold reservoir. So efficiency can be thought of as the ratio of how much you receive, which is work, to how much you have to pay to run the engine, which is the input heat. So you can think of efficiency as that ratio as shown here. So realistic heat engines waste energy in many ways, but we can imagine an ideal heat engine which does not waste energy. So the energy wasted here is not the energy that goes to the cold reservoir, the heat that goes to the cold reservoir. the energy wasted could be friction or many other things. So even if you have an ideal heat engine, it does not work with 100% efficiency. Again, here waste doesn't mean this one, QC, which is given the heat given to the cold reservoir, but it may have certain inefficiencies that waste energy in the processes in the engine. So even if those energy is not wasted in the engine, even in that case, we cannot get efficiency to be 1 or 100%, same thing. So the maximum efficiency is given in terms of reservoir temperatures, which is now instead of Q's, we have now T's. By the way, Tc and T cold and T hot, they must be in kelvins. So those are the temperatures of the hot reservoir and cold reservoir. So the maximum efficiency will be always smaller than 1 because some heat is always given out as heat to the cold reservoir, which is QC. So even if the engine doesn't waste any energy, because this is, the working principle of heat engines is basically taking heat from the hot reservoir and giving heat to the cold reservoir. Remember, there should be some temperature difference, which is the case. So naturally, since Tc is not 0, so it's at some temperature, this number never becomes 1. So this part is never 0. So Emax, even the ideal heat engine, does not work with 100% efficiency. So we can rewrite the efficiency equation now in terms of temperatures. So remember, we had work equals E times Q. So QH. Now, remember, we also defined E as in terms of Q's, but here, now we think about ideal case, where instead of Q's, the ratios of the Q's, we can write E as the ratios of temperatures. Let me go back one slide. So we wrote here the efficiency in terms of the ratio of heat cold and heat hot. But we can rewrite it as, instead of heat in the numerator and denominator, we can also use temperatures by thinking this is an ideal heat engine. But as I mentioned, even in the ideal heat engine, so ideal heat engine means we can replace Q's by T's, the temperatures. But even in that case, as you can see, this E value is never 1, so we never have 100% efficiency. If the hot and cold reservoirs have the same temperature, now let's imagine that we have, let's say 300 Kelvin and 300 Kelvin. So it's both at room temperature. So then it follows that the maximum efficiency is 0, because if these are the same numbers, then you have basically 1, and 1 plus 1 is 0. So then this term, the work done, will be 0. So as a result, the amount of work that such an engine can do is 0 if those temperatures are the same. And this goes back to what I said in the earlier slides. Heat engines require different temperatures in order to operate. So you need delta T not to be equal to 0. So for a heat engine to be able to work, you need a temperature difference. Okay, in this example, it says a heat engine with an efficiency of 24% performs 1250 joules of work. Oh, this is the work, and efficiency is given. So find the heat absorbed from the hot reservoir. So if you remember, the efficiency was about the conversion of the heat that's absorbed by the hot reservoir. So that was related to efficiency. And we wrote work is efficiency, which is smaller the number smaller than 1 times QH. And from here, you can rewrite it as efficiency as work divided by QH, or QH equals work divided by E, same thing. Now, work is given in this problem. Efficiency is given 24%, but you have to convert the percentage to the number, which is smaller than 1, which will be this number, 0.24. And if you do the division, you will find the heat that's absorbed by the hot reservoir. So this heat is 5210 joules. Now in the second part, the heat given off to the cold reservoir. Let's calculate this. And we will use energy conservation to calculate it. Remember, this QH is equal to work done plus the energy given out to the cold reservoir. Or you can rearrange it. You can write it as this way, or you can write it as QC equals QH minus work. And we already calculated QH, Q hot, in the previous part, and work is already given, and you can find QC, which is this value. Or we could calculate QC by using the efficiency formula that's equivalent, and if you do that, you will also find the same number. Okay, here's another example. Which heat engine is more efficient in the idealized case? So the ideals, for ideal heat engines, the efficiency formula is this. And so instead of Qs, we have TC and T hot. So we will basically calculate this efficiency for each case. So in this case, the TH and TC, so this we have 300 divided by 450, and it gives you 33% efficiency. Here we are going to write 1 minus 400 divided by 600, which gives us exactly the same number, 33%. So even though the temperatures are different, but these two engines, they work with the same efficiency. Now we will move from heat engines to refrigerators, air conditioners, and heat pumps. Now remember, heat engines take heat from the hot reservoir, which could be a boiler of a train, for example, and produces mechanical work and gives out remaining heat to the cold reservoir, which is the condenser. Now gas travels from the hot region, which is boiler, to the cold region, which is condenser, spontaneously, which means naturally without any external cause. So as long as you have a hot reservoir and a cold reservoir, you can use a heat engine to create work. So you don't have to provide any energy for the engine to work. It will work automatically by itself or spontaneously. But refrigerators, air conditioners, or heat pumps use work. They don't produce work. They actually use work. As you can see, the work is now an input, not an output. So for these machines, of course, you know what work is here. It's the electricity. So whenever you use a refrigerator, air conditioner, or a heat pump is basically anything that you use to heat your room. So when you use any of these, you know that you have to pay for the electricity because they use work. They don't produce work. So refrigerators, air conditioners, and heat pumps use work to push heat from the cold temperature reservoir. As you can see now, the heat, some heat is taken from the cold reservoir, let's say 100 joules, and electricity is used, let's say how much energy, let's say 200 joules. And the total, so some heat is given out, which will be 300 joules. So they take heat from the cold and give out to the hot temperature reservoir. Now, what is the example of this? For example, for a refrigerator, let's say you put a can of soda or some water in the refrigerator. So it takes heat from the can of soda, the refrigerator, by using electricity, and pushes that heat to the kitchen. And if you actually look at the refrigerator with some thermal camera, or you can even touch the outside of the refrigerator, you will see that it's actually hotter than the room temperature, because what it does is when you put a can of soda, it takes, so let's say the outside temperature is, room temperature is 20 degrees. Let's say a can of soda is now, because it's colder, it's in the fridge, let's say 5 degrees. Now let's say you set the fridge to 3 degrees, so it will still take some heat from here and give it out to the kitchen, the refrigerator. How can it do it? By using work or electricity. So this does not, as we mentioned before, this does not violate the second law of thermodynamics, because this is not a spontaneous process. This doesn't happen naturally. This happens with work or electricity, by means of using work or electricity. So the other thing that we use is the air conditioner. So it takes the heat from the cold reservoir, which is the room, and pushes that heat to the outside, which is outside. So your room is in summertime. If you turn on the air conditioner, maybe it's 18 degrees, and maybe the outside is 35 degrees. So what happens if you open the window? Well, the heat flows into your room. But if you close the windows, the air conditioner will work. It will take heat from your room, and it will pump it out to a hotter temperature. Of course, for that, it has to use work. It doesn't happen spontaneously. It has to work. It has to use some work, which is, again, in this case, the electricity. The other example is basically the heat pump. So it uses the cold outside reservoir. So let's say the outside temperature is 1 degree Celsius. The inside temperature is, let's say, 18 degrees Celsius, so winter time. So the heat pump takes the cold air, takes heat from the cold air outside, and pushes in heat to a hot reservoir, again by using electricity. So back to the refrigerator, it thus, as a refrigerator operates, it takes the heat from the food and gives it out to the kitchen. Again, the food is colder, the kitchen is hotter. To be able to push heat from the cold object, cold reservoir, to the hot reservoir, The only way to do it by basically not producing work, but by actually consuming work. So again, if you look at the difference between the heat engine, where the heat flows from the hot to cold reservoir spontaneously, which means naturally without external cause, it produces work. But in the case of refrigerator, air conditioner, and heat pump, the heat flows cold reservoir to hot reservoir, and the work is used by these machines. So these are not engines. They don't produce work. They actually use or consume work. Now, for refrigerators, there's this coefficient of performance. It's COP. For a refrigerator, it's given by QC, the cold temperature, heat. That's taken, the heat taken from the cold temperature. In this case, the heat that's taken from the soda can within the refrigerator, divided by work. Work in this case is, of course, the electricity energy used. So the typical values for the coefficient of performance range from 2 to 6. If for the same amount of heat that's moved from the soda can to the kitchen by the refrigerator, if the work is less, if you use less electricity, that means the COP number will be higher, right? So that means the refrigerator is more efficient. So by using less energy, it becomes more efficient. So in this exercise, it says the refrigerator has a coefficient of COP. It's just a number, dimensionless. It doesn't have any dimension, 3.25. Why doesn't have any dimension? Because it's energy, heat is energy, work is energy, joules divided by joules, it's a dimensionless number. So for a certain refrigerator, it's 3.25. How much work must be supplied to this refrigerator in order to, so in this case, this is electricity energy, in order to remove 261 joules of heat from its interior? You basically use this equation. So you know the heat that must be removed from the soda can in the refrigerator, and COP value is given. So from here you can calculate the work that must be used by the refrigerator to remove this much heat from the soda can. So the other question may be, okay, how much heat is given out to the kitchen by the refrigerator? Well, again, you have to think of the energy conservation. Here, QC and work, they are inputs to the refrigerator, and the output is QH. So QC is 261 joules. And the work done is 80.3 joules. And if you add them up, you will find 341 joules. And that's the heat that will be given out to the kitchen. So refrigerator, it cools down the things that you put inside. In the heat pump, it's basically it pumps heat to a hotter region. Remember, outside is 1 degree Celsius. Inside is maybe 20 degrees Celsius in winter time. So the natural flow of heat is from inside to outside. Okay, so this is inside your room, and this is outside in winter time. So naturally, it would flow this way. But if you want it to flow this way, so if you want to have your room hotter than outside, then you have to use some energy, and that's the heat pump. Even though these refrigerators and heat pumps They look, in real life, they look different objects, but the principles are the same. So heat pumps used to heat, they're used to heat a room. And for them, there is also a COP value for a heat pump. It's given by this formula. Now, the difference between these two for the refrigerator and the heat pump is, for the heat pump, you use not QC, but QH. And the typical values for coefficient of performance range from 3 to 4 for heat pumps. Okay, now we move to the concept of entropy. It's an interesting concept, and sometimes it's hard to understand when you first learn it. The concept of entropy is a measure of randomness or disorder in matter. Among the solid, liquid, and gas phases, the most random and disordered phase is the gas phase, and you can see it here. The gas particles, they are random, their velocities are random, they are at random positions. But if you look at solid, there's a crystal structure always in the solid phase, so that it's ordered, it's not disordered, and it's not random. So entropy is maximum in the gas phase, high entropy, and it's minimum in the solid case. So one meaning of entropy then, it quantifies the randomness. If there's more randomness and more disorder, there's more entropy. Now, how do we relate entropy to the things that we have been mentioning, like heat and temperature? Well, if a system exchanges heat Q while it's being at temperature T, the value of Q divided by T gives the change in entropy. For example, if ice at 0 degrees melts by absorbing heat from the environment, maybe room temperature, so its entropy increases. So at a certain temperature, so ice is at 0 temperature, it absorbs heat from the environment, and its entropy increases. How much? The amount of increase of entropy is Q divided by T. On the other hand, if you put a glass of water in the freezer and make ice, so you make ice from water, the entropy of water decreases. Why? Because you go from disordered phase to ordered phase. This is ice. Sorry, it's actually going from here to here. So this is water. So the entropy decreases in this if you go in this way. So if you take heat out of a system, the entropy of that system decreases. But the freezer will create entropy to do this work, and we will come to that in the following slides. Even though the entropy of the water decreased by itself turning into ice, but if you think about the entropy that the freezer creates, it's actually more than the entropy decrease of water. So overall, the total entropy, if you think about the water and the ice and the freezer, it actually increases, but we will come to that point. So for now, the definition of entropy change is basically the heat exchanged with the environment divided by temperature. And its unit is, because Q is in joules, it's energy, divided by temperature, which is in kelvins. Now, in this example, in part A, it says calculate the change in entropy when 0.125 kilogram chunk of ice melts at 0 degrees. Assume the melting occurs reversibly. So the word reversibly means no energy is lost to things like friction. So as this melts, naturally, maybe there's some friction occurs because this fluid, on the surface moves out. So you would expect some friction occurs, but if you ignore that thing, those frictions. You can think of this reversibly. That's what it means. So ignore those frictions. So now let's calculate the entropy change. So we have to calculate. So this is the latent heat of fusion. Remember, it was related to the solid, the transitions between solid and liquid phases. So because we're talking about here melting from solid to liquid, we have to use latent heat of fusion. And you can look up that in the table. You will find it to be this number. And mass of the ice is given. If you multiply these two, you find this much energy is needed to melt it. And if you want to calculate the entropy, so you divide this Q, the heat, by the temperature. Temperature is 0 degrees in Celsius scale, but you have to convert it to Kelvin. So it becomes 273 Kelvin. So this is, remember, 0 degrees Celsius. So the entropy change is 153 joules per Kelvin. Now, entropy change is positive. The matter became more disordered, and that makes sense because in the ice, in the solid phase, it had the crystal structure. It was ordered, but when it melted, it became liquid, and now it's more disordered. And the second part, it says, suppose heat is now drawn reversibly from 0 degrees of melted water. So you have now water at 0 degrees, but now you will actually take out heat from that system, causing a decrease in entropy for this much. How much ice freezes in the process? So we can use absolute values if you don't want to deal with the negative sign. So this process happens at 0 degrees Celsius, which is 273 in kelvins. And the change in entropy is this much. From here, you can calculate the amount of heat taken out from the melt water, which is water at 0 degrees, and that heat is this much. Now again, use Q equals M times L fusion, latent heat of fusion. And from here, you can calculate how much of that melt water at 0 degrees is turned into ice, which is this number. So remember, this was the total mass. So this much entropy change only converts only this much of water into ice. Not all of the water is turned into ice because the melt water or the ice water, initial ice mass was this much, which is larger than this value here. So let's continue with the concept of entropy. Energy is always conserved in nature. That's something we repeated in physics 1. But not all energy is usable. Now it's important. Energy may be conserved, but it's not always usable. So energy may turn into useless energy. Even though it's conserved, it may be useless. So for example, energy lost into air drag cannot be recovered and used to do work. If you ride a bicycle, you will, because of the air drag, you will create some turbulence of air back here. And in fact, this is the reason why you have to keep cycling. So if you don't spend energy, so the reason that you're actually spending energy is to win against that air drag. And this is energy wasted to turbulence of air molecules. Is energy conserved here? Yes, energy is conserved. Some of your kinetic energy went into the energy of the air molecules, with the energy of the air molecules. But what happened is, even though energy is conserved, some energy. So this energy in the air molecules, I cannot really use them to do work. So energy turn into some of my energy turn into a useless form. So again, energy is always conserved, but usable energy decreases when we create work. So entropy quantifies how useless the energy of the system. So high entropy means the energy of the system is useless, or to put differently, if you increase the entropy of a system, that means the energy is conserved, but the useful energy is actually decreasing if you increase the entropy. Or in other words, if the amount of useless energy is increasing in a system, that means entropy is increasing. So that's actually why we need the concept of entropy. So we are not only interested in the amount of energy in the universe. See, energy is conserved. The mechanical energy your mechanical energy went into some of it to air. Energy is conserved. But we are not only interested in the total energy. Okay, it's conserved, but sometimes it's not useless. This part of energy is useless. I cannot use it to do work. I cannot turn it into work. So that's why we also need a concept which talks about not energy itself, but the usable energy, or the amount of energy that's wasted. So that's why we need the concept of entropy. Now going back to heat engines, remember they take heat from the hot reservoir and produce some work and give out the rest, the remaining energy that's taken from here to the cold reservoir. So heat engines take heat, Q hot, but cannot turn all of the heat into work because it gives out some part of the heat to the environment. So work equals Q hot minus Q cold. Here QC, Q cold, is the useless energy. Remember, heat engine must give out some heat to the cold reservoir. That's the nature of it. That's how it works. And this energy, it's wasted, it's useless. It's not disappearing, its energy is conserved, but it's useless for us because we cannot turn this into work. Only some part of this QH we can turn into work, and some part of that heat will be useless. So remember, entropy is about the uselessness of energy. If you create useless energy, then that means you create entropy. So we can calculate the entropy created by a heat engine. And this is an example for it. So heat engine produces work, but let's forget about work for now because we will calculate the entropy created. So a hot reservoir at the temperature of 576 Kelvin transfers 1050 joules of heat irreversibly to a cold reservoir at the temperature 305 kelvins. Find the change in entropy of the universe. So the entropy of the universe means the entropy of the whole system. So the entropy of hot reservoir will change. We will call it delta SH. The cold reservoir's entropy will change. We will call it delta S, entropy change for the cold reservoir. And at the end, we will add them up to calculate if the total entropy of the whole system, we can call it universe, if it changes or not. So if it changes, then we will say this heat engine or this process actually creates some entropy. Okay, first of all, let's calculate the entropy of the hot reservoir, the entropy change in the hot reservoir. So change in entropy in hot reservoir is basically Q divided by T, but we will use a negative sign here because when heat is given out, Q is negative. We talked about this in the first slides. When the system gives out heat, we use negative value, and when the system takes heat in, then we would use positive value. So that's that's the reason of negative value, because this hot reservoir, it gives out heat. So in this case, this is not exactly like an engine. So all the heat that's given by the hot reservoir it will be given to the cold reservoir. So no work in this case will be produced. But we can calculate this example even with the heat engine, doesn't matter. So all we do is calculate the change in entropies. So here the entropy change for the hot reservoir is this much. It's negative. Why? Entropy decreased. Why? Because this gets colder. It will get colder when it loses heat. And that makes sense, because if things are colder, if they are getting colder and colder, their entropy decreases. Let me go back to this slide where we talked about this. If they're getting colder and colder, their entropy decreases. That means delta S would be negative number if entropy. So for these processes, entropy will be negative if they're getting colder. But if they're getting hotter, then the entropy change will be positive. So that means if you give heat to the system, you will melt it or you will turn it into gas. That means you will increase its disorder or randomness, which means you will create entropy, because S final minus S initial will be a positive number. So that means a final entropy is greater than the initial, so it's a positive number. Okay, let's go back to the slides here. So the entropy of the hot reservoir decreased because it lost heat. Now, what happens to the cold reservoir? Well, it will get heat, it will receive heat of this much. When you give things heat, you will use a positive number, as you can see here. And because this will heat up, its entropy will increase. And that's why we have, for the cold reservoir, the entropy change is a positive number. Now, let's calculate the entropy change of the whole universe, the whole system. So you would add these two entropies, and the first one comes with a negative sign, the second one comes with a positive sign, but when you add them up, you get a positive sign. So the total entropy change is positive. That means entropy is created. So heat went from the hot reservoir to the cold reservoir through this contact, and this process created entropy. Entropy always increases in thermodynamic systems, and energy usefulness decreases. And again, don't forget, energy is conserved, but what happens is you get the energy usefulness, it decreases. So there's still the same amount of energy, it just goes, the heat goes from here to here, so it's not lost, but the useful energy, the useful energy turns into useless energy, because now these temperatures will get closer to each other as the heat moves from the hot to the cold. And remember, if they're close to each other, and even if they're at the same temperature, this cannot act as a heat engine, because what you need for heat engine to do work, to create useful work, you need temperature difference. So it's a good thing that there is a temperature difference, because I can use it to do work. But if the temperature difference is decreasing, if they're getting close to each other because of this heat exchange, then that means I cannot use it. I cannot use the system to do work. That means even though the energy is conserved, but it turns into more and more useless energy. So that also means entropy increase. So again, entropy does not quantify the amount of energy. Amount of total energy is the same. Entropy quantifies the amount of useless energy. If there's more useless energy, then that means there's more entropy. So whenever you hear the word entropy, you can, in your mind, you can exchange it with the word useless energy or the uselessness of energy. So we talked about order disorder a little bit. So let's talk about it a little bit more. If you have hot and cold bricks, you can see here, you can use the temperature difference to create work. That's how heat engines work. So you can use, so you have hot brick at higher temperatures. So these arrows, they show the velocities of the molecules in the brick. And as you can see, at low temperature, those vectors are smaller. So the low temperature molecules in the brick, they vibrate less. At high temperature, they vibrate more. So those vectors, they actually show vibrations. So, and if you have a system where there's a temperature difference, remember, temperature difference is a good thing, because when there's temperature difference, I can use this as a heat engine. I can produce work out of here. But when the bricks, if I connect the bricks with some other material, then what will happen is that the heat will flow from the hot to the cold brick. When the bricks exchange heat and come to the same temperature, of course, if you wait enough amount of time, they will come, let's say, if this is 100 degrees, if this is 20 degrees, they will meet at an intermediate temperature, maybe 60 degrees. It also depends on their mass, but let's call it 60 degrees. Now both are at 60 degrees. Can I use the system as a heat engine? No, because delta T is 0. So energy is not lost. It went from the hot brick to the cold brick. Now they are at the same temperature. Energy is conserved, but the useful energy or the usefulness of energy is lost. So that also means entropy is increased. We cannot make a heat engine with two bricks at the same temperature. So we cannot use this system as a heat engine because there's no temperature difference. Now, it's possible to cool an object to temperatures arbitrarily close to absolute zero. So absolute zero means 0 Kelvin. Okay. And by the way, this is not 0 Celsius, and in Celsius, it's about 273, negative 273 degrees Celsius. So absolute zero is this or this, same thing. It's possible to cool an object to temperatures arbitrarily close to absolute zero, not exactly zero, but you can get close to zero arbitrarily. Experiments have reached temperature as low as 4.5 10 to the negative 10 Kelvin. But no object can ever be cooled to precisely 0 Kelvin. You cannot go down all the way to 0 Kelvin. You can arbitrarily get close to it in the lab, but it will never be exactly at 0 Kelvin. And that's the third law of thermodynamics, which says there's no temperature lower than absolute zero. So the minimum temperature that you can go down is 0 Kelvin, theoretically. But in practice, you cannot even go down to 0 Kelvin, and that's the second part. That absolute zero is unattainable in the experiments. You can get close to it, but you will never get to 0 Kelvin, precisely to 0 Kelvin. So that's the end of this video. See you in the next lecture.